Hello, let's begin the lecture portion of Math 120, Linear Algebra. We're going to start with Chapter 1, Section 1, Systems of Linear Equations. I'm going to break this section up into several shorter videos. The first deals with some introductory vocabulary, and the later videos will include examples of problems. So let's get started here. 1.1 System of Linear Equations. You are already familiar with elementary systems of linear equations. Here's a very simple example from beginning algebra. 2x plus y equals 3, x minus 3y equals 5. You know how to solve a system of this type. There's exactly one solution to this system, x equals 2, y equals negative 1, and you are all very familiar with the graphical interpretation of this system where each of the two equations has a graph that's a straight line, and the solution is the point of intersection of those two straight lines. Now let's look at another example. Actually, before we go on to the other example, I just want to say sometimes a system of linear equations has no solution, and sometimes a system has infinitely many solutions. In the two-dimensional case, no solution would be when the two lines are parallel to each other and don't intersect. The infinitely many solutions situation is when the two lines coincide. Now we can move on to another example. Here I have three equations and three variables. X plus y plus z equals 2, x minus z equals 4, 2x minus y plus z equals negative 5. This system also has a geometric interpretation. The interpretation is in 3D, 3 dimensions. Each one of these equations has a graph that's a plane in 3D. I think you're familiar with planes from Calculus 3. And so solving the system of equations amounts to finding a common point, a point of intersection of these three planes. And I did not draw a very accurate picture here, just a rough sketch of three planes intersecting in space. And for this system, in this example, the solution consists of the point 1, 4, negative 3. There's actually some nice graphics in the textbook that are much prettier than mine that help you think about the situation of planes intersecting in 3D. Let's move on. Just before we move to some other things, let's think a little bit more about, planes in 3D. When you have three planes in space, three planes might possibly intersect in different ways. They could intersect in one point, but they could also intersect in a line, a common line to all three, or all three planes could coincide, kind of like two lines coinciding in 2 dimensions. So there are more complicated situations is the point I'm trying to make here. And as we move to higher and higher dimensions, the geometric picture can get even more complicated. And how we interpret that is one item that we'll address in this course. Point about notation. Instead of using xy, xyz, or wxyz for variables, we're going to start using subscripted x's. So we'll use x1, x2 for xy, x1, x2, x3 for xyz. This notation allows us to use any number of variables. And so the two examples we started with could be written as pictured here, 2x1 plus x2 equals 3, x1 minus 3x2 equals 5, and there's the other example with planes written with the variables x1, x2, and x3. So the main thing is to get used to the fact that we're not going to use y, z, or other letters. x2 is y, x3 is what you may have thought of as z in the past, and this will allow us to work with x4, x5, x6, and have variables for higher dimensions in a way that's easy to write down. So a linear equation in the variables x1, x2, xn is an equation that can be written in the form a1x1 plus a2x2 plus an xn equals b, where a1, a2 through an and b are numbers. Okay, so that's sort of the abstract definition of what a linear equation is. Let's look at some examples. So just again, this is meant to be very straightforward material. 3x1 plus 5x2 minus a half x3 minus square root of 5x4 equals 10 is an example of a linear equation in 4 variables. Now you should also have some idea of what would not be a linear equation. So 3x1 squared plus x2 equals 9 is not linear. Just notice with the x1 squared that the 1 is a subscript, just denoting that it's the first x variable, and then the squaring is written right above it. Of course, that means we're taking x1 times x1, just like in elementary algebra. Here's another example, x1 minus 2, x1, x2 plus 3x2 equals 6 is not linear. So here, in one of the terms, we're multiplying x1 times x2. In a linear equation, you are not allowed to multiply different variables together. When you multiply 2 variables together, like that x1, x2, we say that's actually a quadratic term, even though there's no square there, because we're taking the product of 2 variables that rises to a second degree situation and is no longer linear. So there's an example of another example of a nonlinear equation. A system of linear equations is a collection of one or more linear equations. Not terribly exciting. A solution to a system of linear equations in the variables x1, x2 to xn consists of a list of n numbers, which I'm going to write here as s1, s2 to sn, that make each equation true when plugged in for the variables. That's totally analogous to what a solution would mean in lower dimensions and in beginning algebra classes. Now, here's a couple words that might be new to you. We're going to say that a system is consistent if it has at least one solution. It might have more than one solution. It might have infinitely many solutions. We use the word consistent for all those different situations. If it has one or more or even infinitely many, the system is consistent. The system is said to be inconsistent if it has no solutions. So it really means nothing other than no solution, and you'll see these words consistent and inconsistent used in our textbook a lot, and you want to get comfortable with them. So that's the end of this first video installment of section 1.1. We're going to move on to an example now and actually work through a problem, but we'll do that in our next video.